Hello, my name is Herschel Dorman, and today we'll be learning about the Vsepr process and molecular geometry. So first off, what we should know is what Vsepr actually stands for, which is valence shell electron pair repulsion. And what Vsepr actually helps us do is it gives us the shapes of molecules, which leads us to molecular geometry. And how we get the shape of these molecules is with the help of electrons from the bonds and the lone pairs, but also from drawing out the Lewis structure, which comes with the valence electrons. So we'll start off with an easy molecule. For instance, CO2. Now, when I said earlier we needed to remember the valence electrons, this is where it comes in when we start drawing the Lewis structure. So, carbon has 4 valence electrons, and oxygen has 6 valence electrons, but there are 2 of them, so there are 12, and if you add these together, we get 16 valence electrons. So now, we need to draw the Lewis structure. So, the first element will usually go in the middle, and then on the outside, we'll have oxygen here and there. And both of these are bonds. So far we have 2 bonds. And each bond counts for 2 electrons. So now we have to take 2 electrons away from 16. So now we have, now we have to take 4 away from 16. So now we have 12 electrons left. So now if we have 6 electrons on each oxygen, that means that oxygen is satisfied now because it has the 8 electrons that it wants. But now we also have to satisfy the carbon, so we put another bond here, another bond here, and then we erase these 2, and now everyone is satisfied. So now, if we have one bond site here and another bond site here, because we're only counting the bond sites, not the actual bonds, then we have 2 bonds, and there are no lone pairs on the central atom. A lone pair would look like this, but over here. So that means that we have 0 lone pairs. So if we have 2 bonds and 0 lone pairs, that means that we have 2 locations in total, and that means that this is linear. So anything that has 2 bonds and 0 lone pairs is always going to be linear. And then it has a 3-dimensional shape, which is basically what the Vsepr process provides. Its shape will look like this. So you have one bond here, another bond here, and you have a central atom, and then you have the 2 oxygens right here. But and no lone pairs. And because this molecule has no lone pairs and it looks pretty even throughout, the polarity of this molecule is it doesn't have a polarity. When we'll do the rest of the molecular geometry in a little bit, but we'll see that anything with no lone pairs has no polarity. So now that you understand the connection between the Lewis structure and molecular geometry, this should be pretty easy from here on out. So let's say we have something with 3 bonds and 0 lone pairs, then that means it's the geometry of the atom is going to be bent or V-shaped, whatever you prefer. And actually, no, scratch that. Sorry about that. It is actually trigonal planar. So what that will look like is it has a central atom right here, and then it has an atom out here atom out here, and an atom right here. So these are the 3 bond sites, and it has no lone pairs. So that means that this one also isn't polar. And from here on out, we'll start to see that there will be groups of kinds of geometry. So we'll see that this one only has 3 locations, and the next one will have 3 locations, and then there will be a group that have 4 locations. So the next one that we have is one that has 2 bonds, and our first one that has lone pairs. And this one is actually called bent or V-shaped, not the one before this. And this one will be drawn with the central atom in the middle, and then it'll have 2 electrons coming out over here. These are the bonds, these right here. And then we'll have one lone pair, which I'll make dotted. Now that, so this is what a lone pair would look like in the Lewis structure, and that is why we have it over here. And the 2-1 is actually polar because it has a lone pair electron, and looking back at it, this kind of looks uneven. Like this side is kind of more positive, and this side is kind of more neutral. Scratch that. Sorry, that was completely wrong. The lone pair. So it's polar because it has this lone pair electron right here, and the bonding electrons right here, and the strength between those offset each other, which makes it polar. So our next molecule has 4 bonds and 0 lone pairs, which makes this guy tetrahedral. And so that means that it has a central atom, and then it will have the dotted line is for 3D effect. It's not because it's a lone pair. And then we'll have one here, and one here. And this one is not polar because it looks pretty even, right? And it has no lone pairs. So this should be moving a little bit faster now. Our next one, since we have all the basics down and why everything is how it is, so this one has 3 bonds and 1 lone pair. The next one, and as you can see, this is also in the category of 4 locations because it has 3 bonds and 1 lone pair. The one before it had 4 bonds and 0 lone pairs, and they both add up to 4. So this one has 3 bonds and 1 lone pair, and this makes it trigonal pyramid. And this one would be drawn like this, a central atom in the middle. And then we have an atom out there, a bond right here, a bond right here, and then we have a lone pair right here. So this one makes it polar because it's clearly not even. Alright, the next one is 2-2, so it's still in the 4 location category. An example of this one, because we haven't had an example in a while, would be H2O. This one is actually also bent or V-shaped. and it looks like this. Central atom in the middle, and then you got bonds over here, and then you have lone pairs over here. And though this one does look even, it is still polar. And after this, we go into the 5 location category. And this one isn't polar because it has no lone pairs. This one is called trigonal bipyramid. And the reason it's called this because tri means 3 and bi means 2. So if you take these together, you get 5. That's a good way to remember it. And then this one looks like a central atom in the middle, and then it has a guy going out here, a bond going here, a bond going here, a bond going here, and a bond going here. It's pretty straightforward. And then the next one we have is 4-1. And that one is called a seesaw. In 3D, it actually does look like a seesaw. I'm afraid my sketch probably won't look that way. So you have a bond going here, bond going here, a bond going here, and a bond going here. And then you have one lone pair out here. And this one is polar because obviously it's not even. There's 4 bonds and 1 electron. Alright. And then we have 3-2, so this is still in the 5 location category. This one's T-shaped. And you could probably tell it's T-shaped in my drawing. It kind of looks that way. So you have a central atom here, and then you have a bond here, a bond here, and a bond here. And you can kind of already see the T. And then you have a lone pair right here, and a lone pair right there. So you can kind of see the T, and that one should be pretty easy to remember. It's one of the more creative ones. And then after this, we have 2-3, which is kind of confusing. And this one is linear. This one also looks the way it's described in its name. So you have a central atom here. And then you have 3 lone pairs this time. One here, one here, and then this one's going to be a lot of dots. One right here. And then you have bonds right here. And this one actually is not polar because it looks pretty even, doesn't it? It has 3 going across this way and bonds going up and down. It looks pretty even, so this one is not polar. And after this, we're almost done here. We have 6 bonds and 0 lone pairs, and this one is octahedral. And even though it's octa, which usually means 8, this one is actually 6, and it's drawn like this. And this one is also not polar. Alright, and only 2 more. So we just left the 5 category, and now we're going to the second one in the 6th category. And so this one's 5-1, and this one's a square pyramid. And since this one only has one lone pair, it's still polar. But it looks like this. Alright. And our last one, but not least, we have 4-2. And this one's called a square planar. And this one has a central atom in the center, as they all do, and it goes out this way. You have a bond going out that way, bond this way, bond this way, and then you have the lone pairs right here. And this one is also not polar because it looks pretty even. You have two lone pairs here and here that are canceling each other out, and then you have bonds here, 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 and here that all cancel each other out. So this one isn't polar either. It's one of the weird ones. But yeah, that's basically it. I'm glad you listened this far into it if you did, and I hope you learned from this. Thank you.